Namaskara. In this session we will continue the analysis of the second algorithm for min-max. The complexity of that algorithm is given by the recurrence equation. T of n is T of floor n by 2 plus T of ceil n by 2 plus 2 if n is greater than or equal to 3, equal to 1 if n equal to 2 and equal to 0 if n equal to 1. Towards this we have defined d of n as T of n minus T of n minus 1. So we get d of 2 equal to 1 and d of 3 equal to 2. And in general d of n is d of ceil n by 2. So the d value is related to something smaller than smaller index. D value of an index is related to a d value of something smaller. So in this way you are keep going through a chain of smaller value. It depends on whether you land in 3 or whether you land in 2. In the process of going down, if you land in 3 then the d value will be 2. In the process of going down, if you land in the value 2 it will be 1. What we have shown is this process iteratively when you apply, if the block Bk which has got the numbers from 2k plus 1 to 2 power k plus 1, 2 power k plus 1 to 2 power k plus 2 power k minus 1, this 1 half and then the other half. All these value will land in 2, which will land in 3, sorry, will land in it becomes smaller and smaller and come to 3 and d of 3 being 2 . For all these things it will land in 2 and d of 2 is 1. This is the reason why you will have 2, 2, 2, 2, 1, 1, 1, 1 or 2, 2, 1, 1 kind of a differences in a block. So we will add blockwise because adding the elements in a block is very simple. Okay. How many 2's are there? You have 2 power k minus 1 2's. How many 1's are there? 2 power k minus 1 1's. Therefore sum of d values in kth block Bk is 2 times 2 power k minus 1 plus 1 times 2 power k minus 1, that is equal to 3 times 2 power k minus 1 for k greater than or equal to 1. So the block sum, I call it as a block sum, is 3 times power k minus 1, because in a block half of them are 2, half of them are 1. Two power k minus 1 of them are 2, 2 power k minus 1 of them are 1. Therefore the block sum is this. Now sigma d of k k going from 2 to n, I write as d of 2 plus sum over b1 plus sum over b2 plus sum over b3 and so on. Okay. Let us assume that n is in the kth block. Let us assume that n is in the kth block. N will be somewhere. Let us assume that. Therefore, your sigma I equals 2 to n of d of I is d of 2, this is separate, 3 4 is sum over di of over block 1, sum over block 2, sum over block k minus 1 plus in the kth block n is located. Okay, n is located in the kth block somewhere. You have to add them, but this is very easy to do. Okay, d of 2 is 1 plus block sum for bk is 3 times 2 power k minus 1. So, this block is 3 times 2 power 1 minus 1 plus in this one 3 times 2 power 2 minus 1, and in this block, in the k minus 1 block, 3 times 2 power k minus 1 minus 1 plus some terms. So, this is equal to 1 plus 3 times 1 plus 2 plus 2 power k minus 2 plus something, and this is 1 plus 3 times 2 power k minus 1 minus 1. This is a geometric progression. This sum is 2 power k minus 1 minus 1, which is equal to 3 times 2 power k minus 1 minus 2. So, this is the block sum up to the end of kth block. All values, the d values summed up to kth block, d values summed up to k minus 1th block, d values summed up to k minus 1th block, d values summed up to k minus 1th block. For example, if you are considering 73, okay, suppose n equal to 73, in which block it will be, what is B1? B1 is 3 4, B2 is 5 8, B3 is 9 16, B4 is 17 32, B5 is 33 64, B6 is 65 128. So, basically n equal to 73 means n is in, n belongs to block 6. So, what I am going to do is that I will find a block sum up to 5. Then I will account for remaining element in the block 6. N is somewhere in the block 6. N is somewhere in the block 6, like 73. In general, if N belongs to Bk, then there are two cases, N is in the first half or N is in the second half. N belongs to 2 power k plus 1, sorry 2 power k plus 1 to 2 power k plus 2 power k minus 1, or N belongs to 2 power k plus 2 power k minus 1 plus 1 to 2 power k plus 1. Either it is the first half or in the second half. Okay. So I have to, so how do I sum? So sigma 2 to n is summed as for 2, only one value, and then block 1 sum and up to block k minus 1 sum plus the remaining values. If it is 73, for example, this is 65 to 128, 73 is here. 65 is split into 65, half of this is 32, all right. So 96 and 97 to 128. 65, 73 belongs here, 73 is here. So to find sum of all the differences, I will find a sum up to the previous block, because block sum has a simple formula, and then I will account for the remaining elements. So all I have to do is up to Bk minus 1, sum of d values found up to Bk minus 1 block, up to Bk minus 1 block of indices. It will be 1 plus 3 times 2 power 0 plus 3 times 2 power 1 plus 3 times 2 power k minus 2, that is equal to 1 plus 3 times 1 plus 2 power k minus 2, that is equal to 1 plus 3 times 2 power k minus 1 minus 1, that is equal to 3 times 2 power k minus 1, 3 times 2 power k minus 1 minus 2. This is the block sum up to k minus 1. Up to k minus 1, this is the. Now if n is exactly a power of 2, what is Bk minus 1? Bk minus 1 is 2 power k minus 1 plus 1 up to 2 power k. So if n equal to 2 power k, if n equal to 2 power k, up to that block sum, nothing extra. The complexity is given by, if n equal to, then T of n is 3 times 2 power k minus 1 minus 2, that is equal to 3 times n by 2 minus 2. because n equal to 2 power k, 2 power k minus 1 is n by 2. Therefore, this is the value we get. T of n is 3n by 2 minus 2, but this is only for powers of 2, not for other values, right. T of n equals 3n by 2 minus 2 if n is of the form 2 power k, not otherwise. So, what is that we have to do if n is not a power of 2? It will be within a block, it will be perfectly within a block, and depending on whether it is in the first half or in the second half, we have to consider the cases. Suppose n is in the first half, 2 power k plus 1 to 2 power k plus 2 power k minus 1. That is, n is of the form 2 power k plus alpha, where 1 is less than or equal to alpha less than or equal to 2 power k minus 1, right. N is somewhere here, n is not exactly a power of 2 like 73, okay, and it is in the first half. If this is the case, then whatever is the block sum up to this, then plus 2 plus 2 plus 2, n is of the form 2 alpha, there will be alpha 2's. Therefore, T of n equal to the block sum up to the previous one, which is 3 times 2 power k minus 1 minus 2 plus 2 alpha. N is 3 times 2 power k minus 1 minus 2 okay, plus 2 alpha, because it is up to alpha, okay. Up to the previous block, it is 3 times 2 power k minus 1 minus 2, and then n is somewhere here, that is only 2 alpha. So, this is so n is 2 power k plus alpha, and T of n is 3 times 2 power k minus 1 minus 2 plus 2 alpha. So, how do you express this in terms of n? We have to get a bound in terms of n. T of n is given by this, n is given by this value. We have to relate these values, okay. First, you notice that alpha is less than or equal to 2 power k minus 1. Therefore, n is less than or equal to 2 power k plus 2 power k minus 1. That means n is less than or equal to 3 times 2 power k minus 1. In order to represent, first we will eliminate alpha, then we will get. Now, we can write like this, T of n is 4 times 2 power k minus 1 plus 2 alpha minus 2 power k minus 1 minus 2. Minus 2 is here. This 4 times 2 power k minus 1 plus 2 alpha. I have 4 power 2 k minus 1, that is accounting for this 3. So, I am writing 3 times 2 power k minus 1 in this way. Okay. So, alright, it's a little, let us write like this. Write this as 4 times 2 power k minus 1 minus 2 power k minus 1 plus 2 alpha minus 2. Move this 2 power k minus 1 aside, that is 4 times 2 power k minus 1 plus 2 alpha minus 2 power k minus 1 minus 2. Okay? But what can you say about this? This is nothing but 2n, alright, because 4 times 2 power k minus 1 is nothing but 4 times 2 power k minus 1 is nothing but 2 times 2 power k. So, this is 2 times 2 power k plus 2 alpha minus 2 power k minus 1 minus 2. 2 power k plus alpha is n, therefore, this is nothing but 2n. So, T of n is 2n minus 2 power k minus 1 minus 2. But we have already observed that here n is less than or equal to 3 times 2 power, n is less than or equal to 3 times 2 power k minus 1. That means n by 3 is less than or equal to 2 power k minus 1. So, I am subtracting a larger number. If I subtract a smaller number, right hand side will become larger, is less than or equal to 2n minus n by 3 minus 2, that is equal to 5n by 3 minus 2. So, 2n is given by an expression, but I have an upper bound, very simple upper bound, 5n by 3. 2n is 6n by 3, of which 1n by 3 is gone. So, remaining is 5n by 3. Okay? It is Tn. Well, I can write Tn purely as a function of n. What is k? See, you look at what is the value of n. N is in 2 power k plus 1 less than or equal to n less than or equal to 2 power k plus 1. So, if you take log, you see that k is less than log n is less than k plus 1. Therefore, you take ceil log n equal to k plus 1. Here you have k minus 1. Therefore, it is ceil log n minus 2. I can write like this, T of n equal to 2n minus 2 power ceil log n minus 2 minus 2. I can write like this. It is possible to write like this, and this clearly shows the gain I have. It clearly shows the gain I have. What was my earlier algorithm? My earlier algorithm was 2n minus 2. Now you see that this much is reduced, right. 2 power ceil log n minus 2 amount is reduced. That is what I am seeing in a different way with a different bound. 2 power k minus 1 is less than or equal to n by 3. So, I have gained at least n by 3. Actually, I have gained 2 power k minus 1. So much I have gained. but that actually means at least n by 3 I have gained, at least. So, in some cases my gain is more, right. The complexity, see, let us summarize. The naive algorithm, naive divide and conquer, had a complexity 2n minus 2. This improved divide and conquer has 2n minus 2 power k minus 1 minus 2. This much has improved, right. But 2 power k minus 1 is at least n by 3. So, I gain at least n by 3. So, this is a more efficient algorithm. From 2n minus 2 algorithm, I have got 5n by 3 minus 2 algorithm. The gain is n by 3. The gain is n by 3. In this case, we have to look at another case. This is the case when n is in the first half, but when n is in the second half, we need to look at the calculations for that, and that is what we will do now. Okay. So, if n is in the second half, that is if n belongs to 2 power k plus 2 power k minus 1 plus 1 2 power k plus 1, then n is of the form 2 power k plus 2 power k minus 1 plus alpha, where 1 is less than or equal to alpha less than or equal to 2 power k minus 1. D of n or T of n is, up to the previous block sum will be 3 times 2 power k minus 1 minus 2. This is the block sum up to this. Then you have 2 plus 2 plus 2, 2 power plus 2 times 2 power k minus 1, and then alpha times 1, because in the second half you have 1 1 1 1 like that. You have to add all the differences. You have to add all the differences. The first half has got 2 2 2 and then 1 1 1. This is alpha, this is 2 power k minus 1. So, this is 2 times 2 power k minus 1, and this is this alpha. Therefore, T of n is 5 times 2 power k minus 1, 5 times 2 power k minus 1 plus alpha minus 2, plus alpha minus 2. So, here n is of this form means n is of the form 3 times 2 power k minus 1 plus alpha. This is the form. Therefore, here you can see this is equal to 3 times 2 power n minus alpha is n plus 2 times 2 power k minus 1 minus 2. That is, in this case, T of n is equal to n plus 2 power k minus 2. Now, we will get a bound for 2 power k. 2 power k is less than or equal to how much? Right? 2 power k is less than or equal to, we have to get a bound for. Now, you see that n is n equal to 3 times 2 power k minus 1 plus alpha. Therefore, n is greater than or equal to, or we put it this way, 3 times 2 power k minus 1 is less than n, okay, is less than n. Therefore, 2 power k minus 1 is less than n by 3. 2 power k multiply by 2, therefore 2 power k is less than 2n by 3. Therefore, 2n is less than n plus 2n by 3 minus 2, which is again 5n by 3 minus 2. Therefore, Tn is always less than or equal to 5n by 3 minus 2. So, what is the in the first case also we have shown less than or equal to 5n by 3 minus 2. In this case also it is less than or equal to 5n minus 3 by 2, 5n by 3 minus 2. Therefore, our improved algorithm, the first algorithm has complexity 2n minus 2, the second has complexity less than or equal to 5n by 3 minus 2, and the net gain is n by 3. N by 3 to 2n is about 1/6, that is 1/6. 1/6 I have reduced, which means about 16% reduction. So, earlier I had 2n minus 2 algorithm, now I have 5n by 3 algorithm. I have gained something. All I have done is I have bottomed at 2. There are 2 cases, okay, bottoming at 1, bottoming at 2. This improvement has given some improvement. I gained about 16%, okay. But now 5n by 3 is an upper bound. Is there a bad example? Is there a worst case example? Is there an infinite value of n for which the complexity is 5n by 3 minus 2? The answer is yes. Actually, it is in the border, okay, because we have seen that that is exactly is contributing. Suppose n equal to 2 power k plus 2 power k minus 1. The block sum up to the previous one will be 3 times 2 power k minus 1 minus 2. Then within the block 2 power k minus 1 times 2, each element is 2, that is equal to 5 times 2 power k minus 1 minus 2. But what is k 2 power k minus 1? N equal to 2 power k means this is 3 times 2 power k minus 1. Therefore, 2 power k minus 1 is n by 3 exactly. Therefore, you have n's for which this upper bound is reached. Therefore, this is the worst case complexity value. For others it may be less, for some n's it may be less, but there is an n for which, there are n's for which you have 5n by 3 minus 2 complexity is reached. Therefore, we have the following conclusion. Our first algorithm is naive algorithm, okay, bottom out for n equal to 1, it will be 2n minus 2. Bottom out the recursion for n equal to 1 and n equal to 2. So lot of recursion related to 2 is avoided, because at 2 also you are not making recursive calls, you are returning directly. So the number of recursive calls are less, the complexity is less, and you can see that the gain is 16%, 5n by 3 minus 2 algorithm. The recursion tree will be smaller. For example, for 12 it will be 6 and 6, 6 will be 3 and 3, 3 will be 1 and 2, 1 and 2, 1 and 2, 1 and 2. This is how the recursion tree is. For 2 you are not going to make a further call, you will return it straight away. You can see the recursion tree is very small, much more compact than the previous one. That is the reason why the complexity is also less. Very interesting, right? So you made one small tweak in your code and that resulted in an algorithm that is more efficient. But to analyze the efficiency gain, you have to go through very interesting detailed analysis, and finally we could conclude that the gain is around 16%. In the next session we are going to work on further gain, right? Why should we split only at the middle? Is there another way in which I can split? Is there a clever split which will give some more advantage? It turns out to be, in this case, there is another way of splitting that is going to give further mileage. In other words, when you are trying to design a divide and conquer algorithm, do not mindlessly split half and half. That is one way of splitting. There may be other way of splitting that may lead to more efficient algorithms. You should explore the possibility of other splitting mechanisms or discovering a clever splitting mechanism. Similarly, do not mindlessly go all the way up to the trivial instance. See where you can bottom out. If there is an earlier closure of recursion possible, it will reduce the number of recursive calls and it will contribute for efficiency. That is what we have seen here. We will continue our next session to design an algorithm even more efficient than 5n by 3 minus 2 algorithm. I stop at this point for this session. Thank you.